Now we're going to look at what happens when we use some of these modes with register 7. Register 7 is the program counter. The program counter is normally updated when we're executing an instruction. Program counter has been incremented to point to the next instruction. It is always incremented by 2 because instructions are 2 bytes. All right, so if I have an instruction at location 1000, when I am executing the instruction, the program counter has been updated to at least 1002. Now, if I use mode 6 or 7, where there is an additional 2 bytes after the instruction to be used with the mode, with a register, you can see them there, register, whatever the register is, plus some 2 bytes, X. In that case, if it's a single operand that uses mode 6, then I'll have 2 bytes following the instruction. That means when the instruction is executing, say the instruction again is at location 1000, the location counter won't be pointing at 1002, it'll be pointing at 1004. Because it sees the mode and it knows there's 2 bytes after the instruction, and the program counter needs to point at the next instruction, not at data. So program counter, if you've used one mode 6 or one mode 7, it means you've got at least 2 bytes after the instruction. If it's a 2-operand instruction and both operands use mode 6 or 7, it means you got 4 bytes. So the instruction's at location 1000. The first set of X for the first operand is at location 1002. Second is at 1004. So the program counter will be at 1006. Program counter is automatically updated by the correct amount when you're using mode 6 or 7. Now the program counter is always going to be incremented by 2. It is never incremented by 1. And the system wants it to be incremented by 2 because instructions go on even boundaries. They're words. All right, let's see what happens when we use mode 2, which is normally called auto increment, on register 7. First of all, we call it immediate. We call it immediate. What does that mean? It means, if we go back to auto increment, means register N contains the address of the operand, then we increment register N. So, in this case, register 7 is the register, and since, okay, let's say we got a simple instruction, it's got one operand, it means that, one operand like this, it means that the program counter has, so again, it started at location 1000. It means the program counter is pointing at 1002. It means that the 2 bytes at 1002 are the operand. And then register 7 is updated by 2 to point to 1004. So it means that the operand itself immediately follows the instruction. So I've got 2 bytes for an instruction, I got 2 bytes of actual data, that's just my operand, and then at 1004 is my next instruction. So program counter, we start the instruction, program counter is pointing at 1002. We use mode 2 on register 7. That tells us that the 2 bytes at beginning at 1002 are the operand. And since it's an auto increment, it increments register 7 by 2, always by 2. Even if it's a byte operand, it's going to increment it by 2. Register 7 has to go up by 2s. Okay, if we use mode 3 with register 7, now mode 3 is auto increment deferred. The register contains the address of the address, then increment the register by 2. And when we use it with register 7, we call it absolute. The absolute address is contained in the instruction. So what has happened? Register 7 has been updated. It's pointing at 1002. 1002 is the address of the address. So at 1002 are 2 bytes, which are the address. These are absolute addresses. They're not relative to anything. And it mentions down the fine print down here, you would use that to address a fixed location in memory, such as a device register that doesn't move around. It's not relative to anything. So when we're in absolute mode, the program counter, again, we're started at location 1000. That's our instruction. Program counter is automatically incremented to be 1002. We execute a mode 3 on register 7. That tells it that the address in the register, register 7, which is pointing at 1002, is the address of the operand, the address of the operand. excuse me. So that 2 bytes is the actual address of the operand I'm going after. So it's absolute. Those 2 bytes are an absolute address. They're not relative to anything. All right, now it's going to get a little more complicated. Mode 6, which is called relative. The extra word is added to the program counter. What we get with mode 6, again, we go to index here. We've got 2 bytes following the instruction. The register is going to be register 7. So in this case here, let's say we've got one instance of relative, one operand that's relative. That means we're going to have 2 bytes after the instruction. So we've got an instruction at location 1000. There's going to be 2 bytes after the instruction, which is at 1002. Program counter is automatically incremented to 1004. All right. So what happens? It means that we take the value in the register 7, which is 1004, and we add to it the contents of memory at 1002, and that sum is the address of the operand. So in other words, the operand is relative to register 7. So the number that means I can move my program around in memory and not have to worry. So in other words, if some operand is 100 bytes from where this instruction is, doesn't matter where you put the instruction or the program in memory, it's still going to be 100 bytes from this location, from this instruction. So everything is relative to the program counter. The program counter has a value only when the program is actually running. So it's program counter relative. Now let's go over that again. We have instructions at a location 1000. We have 2 bytes at 1002. Because of those 2 bytes, and since it is a mode 6, it means that the location counter will be pointing at 1004, which is presumably where the next instruction is, unless we had 2 mode 6s, but let's assume we only got one. It would be further out if there's 2 mode 6s. So the program counter has been updated to be 1004. We take the value at 1002, we add the 2 together, that's the address of the operand. All right. Now in mode 77, mode 7, register 7, relative deferred, it's basically the same idea. It means the 2 bytes following the instruction. Now again, instructions at location 1000, 2 bytes start at location 1002. We take and the program counter has been updated to 1004. We take the program counter plus the value at 1002, add them together, and that's the address of the address. That's the address of the address. And it's relative deferred, as it says here. So those are some complicated modes. This is how they're represented in assembly language. And you could see the PDP-11 had some fairly sophisticated addressing. In a relatively simple and cheap machine. It was not, it was expensive in its day, but relative to a mainframe at that time, it was very inexpensive. All right, let's look at stack addressing. The stack pointer is register 6. It's either written as 6 or more likely as SP. This is the system stack. There's a system stack to handle interrupts and traps and so forth. Your program has a stack to handle subroutine calls and other things. The stack grows from high memory addresses to low memory addresses. So if the top of your address space is location 1000, the stack will grow from 1000 to 998 to 996 to 994 and so forth. So if the stack pointer points to 990 in your program, that means that the elements between 990 and 1000 are in your stack. Each element in the stack is a word. It's 2 bytes long. Any increment or decrement on the stack pointer is always done in units of 2. It's never done by 1. So you add 2 or you subtract 2 because the elements on the stack are always a word. All right, now how does this work? If I've got what we call deferred mode, which is the stack pointer running in mode 1, that means the operand is on top of the stack. So if I've got an add operation and I'm adding to the top element on the stack, I would refer to it as parenthesis SP, and that would generate mode 1 on the stack pointer. And that means that, and you would go down here, here's the reference for the general modes. In mode 1 on some register, it means that the register contains the address of the operand. Oops, I shouldn't have clicked that. Okay, bring that back up. The register contains the address of the operand. So what it means when you're using deferred mode here is the stack pointer contains the address of the operand. In other words, the operand is the top element on the stack. That's what the stack pointer is pointing to. In mode 2, auto increment on the stack pointer, notice it's a post increment. It's a pre-decrement. That's the way auto increment and auto decrement work on the machine down here, the basic modes. But what it means is the operand is on top of the stack, then pop it off. So if I wanted to let again using an add instruction and say one of the operations was on top of the one of the operands was on top of the stack, what I would be doing is I would be using the operand and then after I've used it, incrementing the stack pointer. In other words, popping it off because I'm going to a higher address. I'm removing an element from the stack. So auto increment mode on the stack pointer causes you to use the top element that's in the stack. You could move it or you could add or something like that. And then to adjust the stack pointer by incrementing the stack pointer, which means reducing the size of the stack. Increment means to reduce. Then there's auto increment deferred. It's very similar. The pointer to the operand is on top of the stack and pop the pointer off. The top of the stack is a pointer. It points to the actual operand. So the top of the stack is a pointer. The stack pointer is pointing at that pointer, and and that pointer points to the actual operand. So the top of the stack is a pointer. It points to the actual operand, and then we increment the stack pointer, effectively popping that pointer off the top of the stack because we moved to higher addresses. Then we've got the mode 4, which is kind of the reverse. We push an element onto the stack. We decrement the stack pointer first. Stack pointer decrements first. This is mode 4. You can see down here. We decrement first and then use it as the address. So we decrement the stack pointer and then use the stack pointer as an address. It, of course, is the address of what is now the top element in the stack, because decrementing the stack pointer adds an element to the stack. Remember, the decrements are always in units of 2. The index mode here is we've got a constant, which is 2 bytes following the instruction, and it will be added to the stack pointer. So what does it mean to add to the stack pointer? It means to refer back into the stack. So if the stack is at 990, the stack pointer, and x is 4, you're referring to 994, which is back in the stack. It's at higher addresses. And likewise, and that becomes the operand. And then there's the deferred value, which the value referred to by x plus the contents of the stack pointer is the address of the address. It's the element in the stack is an address, and it points to the actual operand. What are these used for? These are used in program calls. One example is that in a subroutine, when the subroutine allocates temporary data, it allocates it on the stack. It allocates it on the stack. And so you might have some variables, I, J, K, and so forth, and they're on the stack. How you refer to them is from the stack pointer back into the stack to I. So I might be at stack pointer plus 4, and J might be at stack pointer plus 2, and K might be at stack pointer. So they're used very often to map temporary variables or variables local to a subroutine or a function into the stack. So these are using these addressing modes. When they are used with the stack pointer, they can help you push and pop. And that's what the auto increment and auto decrement was really all about to begin with. It was about pushing and popping. Or to go through tables. That's the other thing, of course. Here's an overview of the PDP-11 instruction set. This is from the 1979 PDP-11 handbook. And if you do a Google search with that PDP-11_handbook 1979.pdf, you should be able to find it. It's online. This was about 10 years after the machines were first introduced. They claim they've got 400 unique instructions. That's probably a stretch. It counts all the different addressing modes and variations. One of the things that PDP-11 did, as it mentions here, if you have an instruction add B to A, not a particularly uncommon thing, that is actually done fairly efficiently in a PDP-11 compared to, say, a mainframe. In the mainframe, which had the IBM mainframe at the time, which was the principal dominant machine of its era, the mainframes, you had to load everything, if you're talking integers, you had to load everything into a register, do the operation, and then store it back in memory. And by integers, I mean binary integers. The IBM mainframe has decimal integers as well, and they're handled differently. So using a machine which has a single accumulator, I guess this would be a load of A into the accumulator, add B into the accumulator, and then store B out in memory. The PDP-11 can do that because of its addressing modes in one single statement. There's no load and store. You can add two places in memory. Two places in memory can be added together and stored in memory. The result can end up in memory. It's not a bad feature. Anyway, the overview of the instruction set is there's single operand instructions. There is an opcode and an operand. There's double operand instructions. There's branch instructions. These jump or branched very short distances. They're not. They don't jump very far. I shouldn't use the word jump because that is an actual instruction. The jump instruction or the jump to subroutine instruction can jump anywhere in memory, addressable memory. Trap instructions are used to generate interrupts. And they are used for operating system coordination and so forth. Then we've got miscellaneous instructions that involve memory management and so forth. We're not even going to look at them. And we're not looking at the traps either because they tend to get operating system specific. And then there are instructions that operate on the condition code. Some of the instructions, somebody obviously folded the page here, the single operand instructions, the clear byte, one's complement, increment, decrement, negate, and so forth and so on. Multi-bit shift, single-bit rotate, and so forth. There are some multi-precision instructions, which means basically if the word size in this machine is 16 bits. So if you want to add two 32-bit numbers, you have to add the first 16 bits together, and then if there's a carry, you add that into when you add the second set of 16 bits together, the carry is added into it. So that gives you can do multiple precision arithmetic because you get carry and sign extend. The instruction format for single operand instructions is there's a long opcode. Now remember, everything in this machine is going to be written in octal. Base 8, and numbers 0 through 7. That creates a bit of a problem when you have a 16-bit machine because 3 doesn't go into 16 even. So you're generally going to find a bunch of octal digits and an extra bit at the end here. And that can lead to confusion when you look at the layout. You'll see an extra digit. Well, that's really only a bit, whereas all the other digits probably are referring to 3 bits. Each octal digit is 3 bits. Octal was used in the previous generations, as we've mentioned, and they stuck with it because so many things on the PDP-11 are actually organized as octal. For example, the register number 0 through 7, the mode, addressing mode 0 through 7, and so forth. Anyway, the single operand instruction format has a very long opcode, and then addresses a single operand by register and mode. The top bit here is part of the opcode, but it also indicates whether it's a byte operand or a word operand. These instructions can, like decrement, can decrement a word or it can decrement a byte. That's what the B stands for. So this high order bit actually tells us the difference. The double operand instructions, there's fewer of them, and they're the ones you'd expect: move from one place to another, add, subtract, compare, arithmetic shift, multiply and divide, and also the various bit operations and so forth. The double operand instructions have a layout that looks like this. There's one operand here, with a mode and register. Again, these would be, in assembly language, you'd see these represented as a number between 0 and 7, or symbolically in other ways. And there's the other operand here, and the opcode is in bits 12 through 15. Again, it does have the high order bit, indicates whether it's a byte or word instruction. So we have a relatively small opcode and a relatively small number of actual instructions here. So what is that? 12, 13, 14, 15. There's 4 bits in the opcode. Let's see. It goes on to discuss it there. I'm getting there. These are the branch instructions. You can branch plus or minus, and then it's a byte that's used for the branch. So so you can go plus 127 or minus 128. And it's words, not bytes, from where you currently are, the current value in the program counter. So if you have a complicated program, you might just be branching around jump instructions. Jump instructions can go anywhere. But these are pretty much a usual group of branch instructions for most computers. Branch if not 0, branch if not equal, and so forth and so on. The branch instruction format is, there's your byte, which is the byte offset. And there it is, can go from minus 128 to plus 127 words from the updated program counter. Program counter is, when you run a branch instruction, you got to remember the program counter is going to be updated before the instruction is executed. So the program counter is actually pointing at the next instruction following the branch instruction when the branch instruction executes. So the branch is relative to that location, not relative to the location of the program counter, branch. So anyway, we've got the opcode is bits 8 through 15, and bits 0 through 7 are the displacement, or the branch amount.